Any chance do a stapler?
I don't. Why don't you make sure your name is on each sheet? So here's a pen you can use before. Thanks. Okay, it's time to get started. So welcome to all of you, whether you're physically here in the room or attending online. Let me just quickly remind you that this is the day that your first hand-in homework assignment is supposed to be submitted. So especially if you're attending online, it's easy to forget that. So if you haven't done that already, you should email it to me. The official standard is it's supposed to be in at the beginning of class, but if you're attending via Zoom and you forgot to email it, just get it in, say within 30 minutes by the end of this class, and I'll consider it on time. First of all, I am so pleased. I have the equipment working that it's in the classroom, so I brought all my stuff with me, but it looks like I don't have to use it. And I think you can even do crazy things like this. Let's see. Yeah, and I don't know if that shows up. Let's see. If I switch cameras, woohoo, look at that. Of course, this camera is not made to focus on anything a long ways away, but you can see, here we are. And as you will notice, everyone in this class is, in the physical classroom is just on the edge of their seat with excitement, ready for another lecture. So if you're attending by Zoom, you should feel the same way. Actually, if you're attending by Zoom, maybe even more excited because you get to do things like sip coffee and rock back in the recliner, right? Which does not sound too bad to me right now. Okay, I'm gonna switch over to stay switched over to the document camera for now. And also, I am not very familiar with this. Of course, this is all new setup. I think I can zoom in a little bit if I can figure out how. Advanced maybe. Well, there should be a way. Oh, there's actually a tiny little scroll bar here. I am not seeing a Zoom. Okay. If anybody knows the secret, feel free to tell me and end the suspense. Wait a minute. Maybe it's hardware. Aha, there it is. Okay. All right. Now, for people in the room, can you read what's on here? Is this adequate? Okay. And for people online, can you read what's on the document camera? Give me a thumbs up or thumbs down would be helpful. All right, thank you. All right, tonight we're going to be talking about, primarily we're going to be talking about determinants, Cramer's rule, and revisit the invertible matrix theorem. However, there is a supplement because on a couple of occasions already in the course, I said, well, if a system of linear equations, ax equals b, has two distinct solutions and it has to have infinitely many. And, but both times I said, well, I'll tell you later because I was in a hurry. So I'm not so much in a hurry tonight. So let me tell you, try to give you an argument for that. And what I'm going to do is I'm just going to flip this handout over and work through an example first. And then the actual proof is very short. But if you don't understand what the proof is trying to say, then, you know, it isn't at all helpful. So I'm going to walk through an example. And the example is this. By the way, I try to remember after every class to scan these handwritten sheets. So if you should miss something, just check on Blackboard after the class and it should appear. If it doesn't, send me a message and I'll, as long as I haven't thrown them away, I'll scan them and put them up. Okay, so I've got a system of equations, ax equals b. Here's A, the coefficient matrix. And in this particular case, I've already found a solution. 3 minus 4, 1, that's a solution. So it's one possible value for x. And I solved it again. Of course, in practice, this is not what I did. I cooked up the equation so that it would have a couple of nice solutions. And then I just reveal them here without revealing my process for getting it. Same system of equations, a different solution. So that means I've got a solution here, a solution here. Those two solutions are not equal. So I have the situation, two distinct solutions. And what I want to show you is that if I have two distinct solutions, I can always create infinitely many distinct solutions. So what I'm going to do is this. I'm going to take this second solution here, 1 minus 2, 2, and the first solution, 3 minus 4, 1, and subtract it. So 1 minus 2, 2, 3 minus 4, 1, subtract those, and I get a new vector, minus 2, 2, 1. I call that n. And the reason I'm calling it n here is because it's in the null space of this matrix. But rather than just claim that theoretically, I'm going to show you. So I take the difference of the two solutions and I get this vector right here. Now, let's take the original coefficient matrix, that's this one right here. I'm going to multiply it on the right by this difference of solutions, minus 2, 2, 1. And I got that right here. And sure enough, it comes out to be 0. Now, you know, it's tedious to check the whole thing, but let's check the first row, for instance. I've got 1 times minus 2 plus 0 times 2 plus 2 times plus 1. So it's minus 2 plus 2. Sure enough, that's 0. And if you compute all 3 rows, you'll find that it is the 0 vector. Now, what I want to just observe is that this was completely predictable. You don't actually have to do this calculation to know that this will give 0. And here's why. Let's say this first one here, let's suppose I called that vector the y vector. And I called this second solution here, I call that the z vector, just to give them names. Then, if I took the difference z minus y, which I called n, and multiplied on the left by the matrix A, then a times n is a times z minus y. But then you use a distributive law. That's a times the vector z minus a times the vector y. But a times z, well, z is a solution to the system of equations. So you get this right-hand side, 594, when you take this product. And likewise, you get the same thing when you multiply on the right by y. You get you have solved the system. So it's b minus b, which is 0. That's what the theory tells us should happen. And sure enough, it is what happened if you do the arithmetic. So if you ever have two solutions to a system of equations, call them, for instance, z and y, here and here. I was off the screen there for a bit. Then if you subtract them, you could name them n. And since these are distinct solutions, that won't be the 0 vector. If they were the same solution, of course, you get 0. But otherwise, it's not 0. So now take any solution to the system of equations, say x. It could be, for instance, our first one here, 1 minus 2, 2 would work fine. Take any solution, let t be any real number, and let n, the vector n, be that difference between two solutions that we had before. Then, what about these? If you took a times x plus tn, you are guaranteed to solve the system to get b. And here's why. If you distribute the a, you'll have ax. Well, ax, we said that x is a solution to ax equals b, so that has to turn into b, right? This scalar t can factor out in front, and now you've got an, but what does an give you? Well, an gives you 0. That's how we constructed it. So you'll get b plus the 0 vector, which is just plain b. So this set here, let x be any solution. Any non-zero solution would probably be best, but that's a vector. And t be any scalar, n be a difference of two distinct solutions, then t is just anything in the real numbers. So you get one solution for every single real number there is. Well, clearly that's an infinite set of solutions. And that's essentially the proof. Now, the reason, what I did here, of course, is I proved it for this particular coefficient matrix X. But, you know, the proof, the general proof looks pretty much the same. Suppose AX equals B has two distinct solutions, then I must have infinitely many. Let Y and Z be two distinct solutions of AX equals B. That is, they both solve the matrix equation and Y and Z are different. Set N to be Z minus Y. N is not 0 because Y is not Z. We claim that for any scalar T, Y plus Tn solves AX equals B. To see that, just plug it into the equation for X, into this equation for X, distribute, whoops, I lost an A here. That's supposed to have an A. And then you do just exactly what we did with the specific one. Factor the T out in front, and you'll have AY, well, that solved it. So that's going to give a, good grief, multiple typos here. That's a B. That's a B. So maybe I should rewrite that equation. A times vector Y plus T vector N is A vector Y plus A times the vector Tn. This is the right-hand side B. Why? Because we said that X is a solution. Or rather, Y is a solution. Then this one, you factor the T out in front. It's just a scalar. That's perfectly legal. And then we said, but this is in the null space of A. So this is, in fact, a solution no matter how you pick T, and therefore you have infinitely many solutions. Okay, so in a certain way, it seems a bit strange with linear systems. You know, if you're just used to, oh, I don't know, like the problems you solve in calculus or something, there's lots and lots of examples where you have maybe 2 solutions but not 3, or you have 3 solutions but not 4, right? So a finite set of solutions, which does not extend to an infinite set, you see that all the time until you get to linear algebra. And when you're solving this kind of a problem, you're going to have no solutions at all, one unique solution, or infinitely many solutions. There is no other possibility. Why? Because if you got 2, you have to have infinitely many. All right. Okay, so that was the thing that I have been putting off for a week, and now it's done.
Is that in our notes? Is that in our notes?
It is posted to, Blackboard, but of course it has some typos in it. So
Okay.
I'm making a note to myself to edit the online version. By the way, I remember when I was an undergraduate, long ago in the Pleistocene, and I had a professor of chemistry because I was a chemistry minor, and he was bemoaning the fact that he had this set of notes that went with one of his classes, and he says, you know, this is just a continual cycle of fixing. And I said, well, what do you mean? put it out, and then if there's errors, you fix them, and then you're done, right? And he said, well, no, because every time we edit, I think the whole department contributed to this document. He says every time we edit, then the secretaries make new mistakes fixing the stuff. And then, of course, we think of things we should have said, so we add a paragraph here and there. And then we introduce errors in there too. So every edit cycle not only takes out some errors, it puts in some errors. And I have found that to be exactly true. I have been working on these stupid notes for I don't know how long, and they are still riddled with typos. And and that doesn't count just the things I said that were stupid, and I should never have said them in the first place. So every semester I find some of those too. I read it and I think, why did I put that in there? So delete that. And I think of something else stupid to put in there for the next time around. Okay, so here we go. Determinants, Cramer's rule, and the invertible matrix theorem. We've been over quite a bit of ground so far. This is a list of things that we've looked at. And by the way, this document, of course, is posted to Blackboard as well. You can download it. I don't know if I want to read through the whole thing, but certainly we've spent some time row reducing matrices, reading solutions from the row reduced echelon form. We learned that if you have an inverse to a matrix, then AX equals B has a solution, a unique solution, and you can write it as X is A inverse times B. Matrix and matrix vector algebra is weird in this sense. Multiplication is not commutative. Just because A times B is defined does not mean that B times A is defined. And even if they both are defined, it does not mean that they're the same size, nor that they have the same contents if they are. So that's really something to get used to. So watch yourself. It's very easy to subtly make that assumption, like when you're writing down an argument. And then you come back later and you look at it and think, I knew that. You can't do that. Well, yeah, well, the thing is, in regular real number algebra, it's no problem, right? X times Y and Y times X are always the same. So we just get in that habit, and it's easy to walk right over that one. The invertible matrix theorem gives a whole list of things that are equivalent. In other words, I think by our final version of it, it's got like 12 or 14 things. And if any one statement in the list is true, they're all true. If any one statement in the list is false, they're all false. So we'll come to that again at the end here. Now, determinants are the next focus. And a determinant is a real number that's computed from a square matrix. And there's an official definition of a determinant, which is simply this. The determinant of A, here's the symbol. It's either det of A, or you write the matrix and then put something that looks like absolute value symbols around it. If you're writing down a numerical matrix, this also works. Instead of writing square brackets and then putting in the entries, you just put in the vertical bars and put in the entries. If you see that, it does not mean the absolute values of all the things in here. It means a determinant. Okay, now I will come back to that official definition, but I think it's going to be easier if I give you some examples first. Okay, so how are determinants computed? Well, that is a loaded question, because we're going to talk about, I think it's 4 different ways of computing determinants. So what I'm going to tell you first relies on the definition. However, by the end of the page, by the end of this page right here, we're going to conclude that this may be a good definition, but it's an absolutely horrible way to do calculations. Okay, so for small matrices, you can make it work. But if you had like a 10 by 10 matrix, I think it's over 6 million different products you have to compute, each one of which has 10 factors. So you probably don't want to do it that way. Okay, so the definition of determinant of a square matrix is this. It's simply the sum of the signed elementary products. So how do you find the elementary products of a matrix? Well, and furthermore, the signed elementary products. Turns out if you have a 2x2 matrix, there's really a quick trick. So this is the standard way of writing down a general 2x2. By the way, I've mentioned this before, but let me say it again. Row always comes first and column second. So row 1, column 1, row 1, column 2. This is row 2, column 2, etc. So if you simply take this product here and call it positive, and this product here and call it negative, that's the sum of the signed elementary products. Now, so for instance, if you have this matrix here, for a 2x2, it's really easy. It's just 5 minus 6, negative 1. That's the determinant you're done, okay? Now, what if you have a 3x3? Well, the signed elementary products turn out to be these. And let me tell you what to look for so you know whether you've got them all. First of all, you notice that every one of these, just ignore the second subscript for the time being. The first subscript are 1, 2, 3, 1, 2, 3, 1, 2, 3, and the same all the way through here. So what I'm doing is I'm picking an element in the first row, the second row, the third row. The first row, the second row, the third row, okay? Now, what about these other guys? Well, what we're doing then is we're starting with sort of like this blank form. A 1 blank, a 2 blank, a 3 blank, and we want to fill this in such a way that we have a permutation of 1, 2, and 3. So in other words, you have to use 1 a single time, you have to use 2 a single time, you have to use 3 a single time, but you can use them in any order. So what are the possible orderings of 1, 2, 3? Well, 1, 2, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, 1, 3, 2, and 2, 1, 3. Okay, now exactly half of them I've labeled as negative, and exactly half of them I've labeled as positive. So how do I decide? What I do is count the number of inversions. This one, we say, now I'm just looking at the second subscript because I've arranged these so that I have first row, second row, third row here. Of course, I could rearrange, but then I'd have to start counting inversions from that too. So the idea is you put them in a standard way so that you get no inversions from the row index and all the inversions come from columns, makes them easier to count. So what's an inversion? This one has no inversions because in every case, the lower subscript comes before the greater one. In this one, however, let's see, 2 comes before 3. That's fine. That's the order they're supposed to be in. But 3 appears before 1. That's an inversion. And that's the only inversion there is here. So this one has, whoops, wait a minute. That can't be right. 2 comes before 1. And 3 comes before 1. So this one has 2 inversions. And therefore, the sign of this product is -1 to the 2, which is +1. This one has 0 inversions. So its sign is -1 to the 0, which is +1. And how about this one? Well, 3 comes before 1, that's an inversion. 3 comes before 2, that's another inversion. 1 comes before 2, that is not an inversion. So the sign of this one is -1 to the 2. I had 2 inversions. And therefore that one's positive. These should all have an odd number of inversions. So let's check. 1 comes before 2, not a problem. Whoops, I'm looking at the wrong one. 3 comes before 2, that is an inversion, 1. 3 comes before 1, that's another inversion. 2 comes before 1, that's 3 inversions. Minus 1 to the third is -1. That's a negative elementary product. 1 comes before 3, no problem. 1 comes before 2, no problem. No inversions there. 3 comes before 2, 1 inversion. Minus 1 to the 1 power is -1. And finally, 2 comes before 1, that's an inversion. 2 before 3 is not an inversion. And 1 before 3 is not an inversion, so that has 1 inversion. And minus 1 to the 1 power is negative. So that's where those come from. Now, you can imagine, what if you had a 4-dimensional matrix? I wrote out the orderings of 1, 2, 3, 4. So if you really wanted to do it for a 4x4 matrix, what you would do is you would write out sort of a blank form like this. Then you'd think of all of the ways to fill in the stars. Here they are. Then for each one of those, I think there are 24 there, and you would find out that exactly 12 are positive and exactly 12 are negative, and you'd figure that out by counting inversions. Of course, if you're like me, you will make a mistake when you do that. So when you get to the end, you'll end up like with 14 negative and 10 positive, and you'll think to yourself, that can't possibly be right. It's got to be half and half. So you go back and do it all over again. And then now you make new mistakes. And after the 6th or 7th time, you'll say, I'm pretty confident I figured it out. But this should convince you by itself, you don't want to do a 4x4 matrix this way, right? You don't want to find its determinant this way. It's just too hard. And I did the calculation. I don't mean I computed a determinant this way. It's an n by n determinant has n factorial signed elementary products. So a 10 by 10 matrix, which by the way is absolutely tiny compared to what working engineers and scientists are working with all the time, that comes up with over 3.6 million signed elementary products. Bad idea. We do not want to do all that calculation to come up with one number from a matrix. So we're going to learn other ways, but at least you know that the sum of the signed elementary products, that's the official definition, and that is actually useful in theory. It is not so useful for calculation. Now let me show you how you can get them with a 3x3. So we've got this 3x3 here. How did I come up with this list? What I did not do is start with this blank form, think of, these many ways of filling it out, and then count inversions. That's not what I did. There's a quick trick for a 3x3. You start with your original matrix, and then you copy your first two columns over again off to the right. And then you take products down these diagonals. That one, and that one are all the positive signed elementary products. And that one, and that one will give you all of the negative signed elementary products. So if you ever did come across like a homework or a test problem that said, give me the signed elementary products for this 3x3 matrix, you would probably do something like this, because it's way faster than just trying to create all these and then error check them and patch them up. So this is what I would do if I had to do that. In the real world, though, nobody computes determinants by signed elementary products. It's a useful theoretical construction. It is not a useful strategy for computing determinants. So what do people do? Well, if you have a 2 by 2 matrix, they do this. This product minus that product. I suppose that is from signed elementary products. But for 3 by 3 and larger, it almost always, you're going to do something else.
What about the A21 and A22?
Say it again, please.
In these products that you just showed us, there are two elements that were left out, the A21 and A22. No, I've got the paragraph with the.
So just tell me up or down from here.
Yeah, so in this matrix, there are two elements that were not touched, I think.
Oh, they are used. Okay, so this A22, see, this is a copy of these two columns are copied here. So A22 gets used up right here.
Oh, I see.
Uh-huh.
Okay, so
And likewise, A21 gets used up right here.
so we don't have to calculate the A12 times A21. That's just
Yeah, you only go down the diagonals where you have 3 elements on the diagonal. So like this pair and that singleton don't get used.
Okay.
Yeah, and by the way, this is just a mnemonic. It's a trick and is no good way to generalize it to a 4 by 4 matrix. Too bad, but there isn't. So, you know, it's just a coincidence.
Would doing the 3 by 3 be that instead of having 6 elements, could you have 3 like you would with a cross product from Calc 3? Where you have like,
Expand on that.
like if you call like A11, A12, and A13 I, J, K.
Yes, there is something like that. That's called a cofactor expansion, and it's on the next page.
Oh,
So yes, that's a good pattern to notice. Okay, so if you had to compute one by signed elementary products, what you would do, and the only reason I'm listing this is because I think there's one in the homework. Whoops, it's here and here. So what I would do is just take these products, 3 times 2 times 1, 6, 1 times 1 times 2, 2 times 1 times 0, 0. Then the negatives across here, 4, 0, and 1. So there's the determinant. 8 minus 4 is 4, minus 1 is 3, if I didn't botch it up. Now, of course, there's another way, right? And this is a good way to make sure I didn't botch it up. Although, in some ways, I'm reluctant to do this because if I did botch it up, then my inclination is to figure out what did I do wrong, and that wastes time. Okay, so we're going to edit this matrix, and let's copy this one in. 3 by 3. It is 3, 1, 2, 1, 2, 1, 1, 0, 1. And now I should have my matrix. I have gotten into the habit with calculators. I find it so easy to push the wrong key. Is just to double check. You know, before I end up wasting a half an hour figuring out why it's not working, only to find out later, oh, I didn't enter the matrix right. So if that's not an issue for you, then you don't need to worry about it. Okay, so this first function under math here is the determinant function. So DET, then go back to the names, copy the A in, close up the parentheses, and to get 2. Oh my. I don't see it. Huh. Well, did I add them up wrong?
I think you copied it wrong on the page. 311, not 312, 120, and the gray area.
Oh, look at that. Thank you. And that makes this 2 times 1 times
On
1.
the bottom, it's on the bottom. It's 120, that column, you gotta flip that one, 311, going down in the gray area.
Yeah,
So the first column, 311. So that column right there should be 311 going down.
it should. First of all, you're right. But it doesn't matter because I never use it.
Oh,
But this error does matter.
That one.
That should be a 2. So 2 times 1 times 1 makes this subtract 2, which turns that into a 2. And now they agree. 311 is copy here. 120.
Yeah,
Ah, it is 120.
you do use it on the 2.
Oh, I use it
Plus
here.
1.
Yeah, you're right. You're right. Anyway, how about this? Now it's right. How do I know? Right there. Proof. Okay. Now, the comment here is that most people don't take a huge amount of this practice to figure out this is a really bad way to compute determinants. Can we think of something else, please? And the answer is, well, of course, number one, I did show you this, right? We have a calculator, and under a lot of circumstances, that's actually a pretty good way to do it. Now, calculators are good for moderately sized matrices. In other words, not so large that you can't reasonably type them in and look at them on the screen and make sure you got the right thing typed in. Another possibility, of course, is with MATLAB. Let me see if I can share my screen. Okay, so for instance, do I have anything in here? No. So this particular matrix, 3, 1, 2, 1, 2, 1, 1, 0, 1, and same command, det A, and sure enough, it's a 2. Now, I should mention this in class. If you use octave is what this is, it is case sensitive. If I tell it find det A where I use lowercase a, that's an error because I don't have anything stored under lowercase a. So it has to be the uppercase, and then it'll work. So, and by the way, you can look at what's in memory. You just type the name and hit return. It'll display it. So A is that matrix. Lowercase a is undefined. Okay, so what else can you do to compute determinants? Well, let me see what I've got in here. You can use row reduction, and you can use cofactor expansion. Now, where did I put cofactor expansion here? Did I put cofactor expansion in here? Oh, yeah, right there. Okay, so let me describe this by means of an example first, and then I'll talk through the general description. Suppose you wanted to compute this determinant by means of cofactor expansion. What you do is this. First of all, we are going to pick any row or any column, and we're going to do what we call expand along that row or column. So let's suppose, for instance, we're going to go along the first row. Now, the cofactors are like the signed elementary products. They have a sign, and it's based on their position. So it's this one starts as plus, then minus, plus, et cetera, all the way like a checkerboard through the system. Now, if you know the row and column, if you're looking at row I and column J, you don't have to draw the checkerboard to figure this out. It's -1 to the I plus J power. And if you think about it, that's the 1, 1 position. So it's -1 to the 2, or +1 is the sign of that cofactor. So you can get that pretty quickly. So I'm going to have 1 plus 1 times a cofactor. I'll just leave a space here for a bit. And then I'm going to have -2 times a cofactor, and I'll leave a space there. And then I'm going to have +3 times the cofactor. Now, what is the cofactor? It is a determinant of 1 order smaller than what you're doing here. So for 1, you find its cofactor by doing this. You strike out, this is the first row and first column. So you strike out the first row and you strike out the first column. And what's left is this submatrix 5, 6, 8, 10. Then likewise, can I make this work? For the 2, I'd strike out the first row and second column, and what would be left would be 4, 6, 7, 10. And finally, strike out the first row and third column, 4, 5, 7, 8. Now, if you were doing a 3 by 3 determinant, you can easily finish this without doing any more. You've got what? 50 minus 48 or 2. And 40 minus 42, -2. And 32 minus 35, -3. And so what do we have here? 2 plus 4 minus 3, 3. So, no? Where's the problem?
Would that be a -9? Would that be a -9?
Right, it is, yeah. 3 times 3 is -9, of course. Okay, one more time. 8 minus 9, I get -1. We agree now?
What would it be in negative? It would be -3.
I'm multiplying. 6 minus 9, -3. Okay, this time, because I'm so confident, I'm going to write in pencil. We good? Okay, and I would, but I don't want to spend another 5 minutes fixing it up. Plug this in the calculator and check it, and you find out what it is. Okay. All right. Now there are some useful facts about determinants, and the reason I'm doing these before I do computing determinants by row reduction is because these are the facts that we use when we're doing row reduction in order to compute determinants. So if you exchange any two rows or any two columns of the matrix, that multiplies the determinant by -1. So when you're computing determinants, is it legal to flop around to exchange the locations of a couple rows or a couple of columns? Answer, yes, you may. When you do it, you've just multiplied the determinant by -1, but that's okay. You know, you make the switch and then you stick a minus on the outside, or if before it was minus, now you turn that into a plus and everything's fine. So you just keep track of the fact that particular operation of interchanging rows multiplied by the determinant by -1. If you multiply it by -1 a second time, you've made no change. Okay, multiplying any row or column by a fixed constant multiplies the whole determinant by that constant. Now, do be careful. There's a tendency when you first hear this to think that means, okay, I've got a matrix here, and I'm going to multiply the whole thing through by 6 because I had some of my entries had denominators of 2 and some of them had denominators of 3, and now I've wiped this out. Except I multiply it by 6, so I'll just put a 1/6 out in front and I'll be good to go. No, if you multiply the whole matrix through, then by say 6, you've multiplied the determinant by 6 to the n, where n is the number of rows, or n is the number of columns. You know, they have to be equal, it has to be squared. So multiplying a single row or column by a constant multiplies the whole determinant by that constant. If you want to do it, go ahead. If you multiply a row by C, then you just multiply the outside by 1/C, and you've canceled out the effect, and everything's cool. Adding a multiple of one row to a different row, that does not change the value of the determinant, remarkably. So if I multiply a row by, say, -2, I multiply the whole determinant by -2. But if I multiply a row by -2, take that result, add it to a different row, that doesn't make any difference to the determinant, which is great because it means you can do row reductions to get zeros, and zeros makes the multiplication easy even for me. As long as there's enough zeros in the factors, I will get it right. Okay, so now I'm going to tell you one last trick, and then we're going to start computing by row reduction. The transpose of a matrix is obtained by interchanging the rows and columns of a matrix. So for instance, notice I have first row 1, 2, 3 here. I have first column 1, 2, 3 here. Second row 4, 5, 6. Second column 4, 5, 6. Third row 7, 8, 9. Third column 7, 8, 9. Another way of thinking about this, which actually works better for me, is I think of that as being on an axis, and you just rotate it around that axis, and this 3 will rotate down to here, this 2 will rotate over here. The things on the diagonal will stay right where they are. You can think about it any way you want, just as long as you get the right answer, okay? So that's what a transpose is. Taking the transpose, well, here's the theorem. The determinant of A and the determinant of A transpose are exactly the same thing. And if you ponder on what happens to the signed elementary products, that won't surprise you. You get exactly the same signed elementary products after you take the transpose. The row, it's like your entry A21, well, that turned into A12. Well, you get the same number of inversions, you get exactly the same inversions. You just look at the first entry instead of the second. And the products are all the same. So, by the way, this is a very useful definition. We actually make use of this later. Matrix is symmetric if its transpose is equal to itself. Putting a T in that superscript position means the transpose. Just a side note for scientists and engineers, if you write this, well, I think there's more than one symbol, but this is one of them, A star, that means you take the transpose and the complex conjugate. For the most part, we are going to ignore the possibility of having complex numbers in the matrices we work with. Basically, all the theory you learn is just going to work except over the complex field. But there are some cases where in the complex field, rather than taking transpose, you take the conjugate transpose. And someone will tell you when you need to know about that. It doesn't come up in this course. Okay, so now let's compute determinants with row reduction. And I am going to do my best to compute these things by row reduction methods. So let's start with this big matrix here. Now this one is, this is big enough that it won't be fun if it turns out that this is ugly. And I brought some line paper because I have a hard enough time keeping things lined up with this stuff. And you will infer after a couple of steps, oh, he cooked the books on this one. He made it come out nice. Yeah, I did. All right, so I want to compute that determinant. And let's see, this goes with page 5. What you want to do is just all the usual stuff where you take a multiple of one row and add it to another to get zeros. Now I've got a leading one here already, so I think I'm just going to stick with that. And so these two determinants are going to be equal. Every once in a while, I'll do something that will change the value. And so I'll put some factor out here to make up for that, and everything should be great. Okay, so the first time is the first row I'm not going to change. And I'm writing for my own use the fact that I want to multiply this by -2 and add it to that. So when I do that, -2 plus 2 is 0. -6 plus 5, -1. -2 plus 2, 0. -2 plus 2, 0. Well, this just got a whole lot better, right? I could, for instance, do a cofactor expansion across this row. And, you know, I would knock it down to a 3 by 3 in just that couple of steps. But I'm going to keep going. So after this, I'm just going to take this row minus this row minus this row. So 1 minus 1, 0. 3 minus 3, 0. 8 minus 1, 7. 9 minus 1, 8. Then 1 minus 1 is 0 once again. 3 minus 3, 0. 2 minus 1, 1. And 2 minus 1, 1. Well, it turns out we're almost done. And the reason we're almost done is there is a theorem, which I didn't mention yet, that says this. If you have a diagonal matrix, whoops, that's the wrong word. If you have a triangular matrix, that means everything below the main diagonal is 0, that would make an upper triangular matrix. Alternatively, if everything above the main diagonal is 0, that would make a lower triangular matrix. If you have either one of those, if you have a triangular matrix, the determinant is the product of the numbers down the diagonal. And we're almost there. If I had a 0 here, I would be there. So now that one's not so easy to pivot on though. So what I'm going to do is actually, I'm going to pivot on this one. So I'm going to take -7 times this row, add it to this row. And when I do that, I'll get, I'll just leave this one alone. Really all I need is that 7, and everything else I'll just copy. I hope correctly. Okay, so these zeros won't impact those. That's done. -7 plus 7, 0. -7 plus 8, 1. And now I want to interchange these two rows. And there's a rule that says when you interchange two rows of a determinant, you change its sign. So that's going to change its sign once. If I change its sign a second time, then, you know, everything's fine. 1, 3, 1, 1. 0, -1, 0, 0. Then those two interchange. So 0, 0, 1, 1, and 0, 0, 0, 1. I now have a triangular matrix. So my product is this times this times this times this. So it's the negative of 1, -1, 1, 1. So I can compute that determinant by row reducing to triangular form, then take the product down the diagonal, and I'm good. So, for instance, if I had this matrix, that determinant, you just take the product down the diagonal here. Well, 2 times a half is 1, this is 5. So if you're doing it by row reductions, usually the strategy is row reduce towards a triangular matrix. Once you get there, take the product down the diagonal and you're finished. You don't need to go any further.
That works for any size matrix.
Yes, it does. And by the way, if you needed to compute determinants and you were, say, writing the code yourself in C, this would be one reasonable strategy. You would actually do the row reduction, and then, you know, you'd have to, in your code, you have to keep track of when you did any of those operations that change the value. So like if you interchange a couple of rows, multiply your multiplier at the end by -1. And you could do something like this, you know, if you wanted to, you could say, suppose this were 2, 8, 6. You could say, well, that whole row has a 2 in it. Let's factor it out. That'd be fine. And just put that 2 in your outside multiplier. And those kind of strategies work very well.
So you'd have to take it out and then multiply it by n to the exponent to n.
Yeah, let's do one, okay? Okay, so suppose I had this one. Of course, it could be much more complicated. Same things are legal. But I could look across here and say, oh, look, every single thing in that second row has a factor of 2. Wouldn't it be simpler to Well, there's two ways to reason it. Reason number one, I could factor a 2 out of that row. So then that means I have a 2 on the outside. Now 2 comes out of this. In the same way, you could look at this and say, hey, there's a 3 in there, so let's factor it out. And then you can take the product down the diagonal, 5 times 6, 6 times 5, 30. I took a 2 out of this row. I took a 3 out of this row, 2 and 3 on the outside. Alternate way of thinking about it. I multiplied this row by 1/2. When I did it, I got this row here, but when I multiplied this row by 1/2, I multiplied my determinant by 1/2. So I put a 2 outside to make up for that. Similarly, when I multiplied this row by 1/3, I cut the value of my determinant by 1/3. I'll multiply by 3 to make up for that. Okay. And by the way, row reduction is a relatively efficient process for matrices. Any kind of row reduction strategy is going to take on the order of n² operations. And if you're just going to triangular form, it's not n². It's like n² over 2 or n² over 3 or something like that. And if you think about it, you've got a matrix has n² elements in it. So how could you get the computation cheaper than that in the worst case? You have to take into account all the values. So you're doing pretty well with row reductions.
I have a question. So for whatever reason, can we take a factor out of a column?
Yes. And this is the really nice thing about computing determinants. Anything that's legal with rows is also legal with columns. And here's why. So for instance, you could look at that and say, gee, most of those entries would be pretty nice if I divided that by 3. I'd get one fraction, but everything else would be cool. So can I factor a 3 out of that column? Yes. And even if we didn't have that theorem yet, we could reason this way. Well, the transpose of this matrix and this matrix have the same determinant. So let's transpose it. Then this becomes a row. Then it's legal to take the 3 out. And then you think, well, actually, I liked it better the other way. So you transpose it back. So sure, absolutely legal. Okay, now, the last thing I want to point out is that every once in a while, you do come across a determinant that you need to compute that you can't just dump in the calculator. These sorts of things do come up in practice. So what do you do if you have something like this? Well, you know, frankly, there's no nice way of working on it. It's going to be a mess no matter what. However, you do have some options. Number one, you could use signed elementary products, but we've already sort of learned that usually that's a bad idea, so probably we won't go for that strategy. Strategy number 3, I guess, the one that we looked at was, well, you could row reduce. Well, row reduction might be a little bit ugly with something like this, because you're going to tend to get fractions with k minus 1, k minus 3, or k minus 4 in the denominator. So, you know, maybe you could avoid that, but, you know, it's not really exciting. So row reduction sounds like it might get messy. The other possibility is you could try a cofactor expansion. And, you know, that doesn't really have much of a downside. Now, it still will be a mess, but so what I'm doing is working on this guy right here, okay? So let's go after that one, and I'm just gonna write it out. Oh, I forgot to mention it. I'm sorry, I can't think of your name.
Dustin.
Dustin, you asked earlier, is there anything you can do sort of like the cross product? And you saw that really, if you had I, J, and K here, you do exactly that trick.
Mhm.
What you're doing essentially is cofactor expansion. So the direct answer now is yes. Yeah, you're exactly right. That is the same pattern. Okay, so if I want to do this by cofactor expansion, remember we have signs involved, plus, minus, plus. So if I want to do it by cofactor expansion, you don't have to do it across the first row. You could do it over any row or any column. Doesn't make any difference. But none of them seem to have a real advantage to me over the first row. So I'm going to take that one. So K minus 1 times its cofactor. Its cofactor is the determinant of this submatrix here. K minus 3, 4, 4, K minus 4, determinant. Then negative 2 times the determinant that you get by taking out the first row and second column. So 2, 4, 3, K minus 4. And let's see, the last term is plus 3 times the cofactor comes from this submatrix, 2 K minus 3, 3, 4. Now, I don't think I agree with that. Let me try this again. Oh, I do. Yeah, okay. Gee, what a mess. Now, you could, I suppose, get a little cleanup here. If you added this row to this row, you'd have just K instead of K minus 4, which may be an advantage in the algebra later on. On this one, I don't know what you could do to make it nice. I think it's just not going to be nice. So let's go ahead and write this out as algebra. This times this, K minus 3, K minus 4, minus this times this, 16. The next one, I'm inclined to take that simplification. Is it really going to help? I'm not sure, but I'm going to add the first row to the second. And the advantage I see is I just have a single term here. And the last one, yeah, probably not much I can do to help it. Eight minus 3 times K minus 3. Okay. Well, K minus 1, K minus 3, K minus 4, minus 16 times K minus 1, minus 2 times 2K minus 20 plus 3 times, well, why don't I just multiply this out? 3 times 8, 24 minus 9 times K minus 3. And Yeah, oh, nice. I think, you know, I could spend 30 minutes on this trying to make it look pretty, and it still wouldn't. But I can maybe make a little bit of progress. Minus 4K plus 40 minus 9K plus 27. And then, you know, there's a couple of obvious pieces you could put together. So you get the constants and the K terms together, and then you'd have that product, and I don't know, you kind of, I guess at that point, it would depend on what do you want to do with this expression. So if you're trying to figure out where it equals 0 or something, then you probably got more work to do. But if you just want to be able to evaluate it for several values of K, that one more step would be good enough.
Does the code factor extension work on bigger matrices, like 5 by 5 and so on?
Yes.
And how does the time go?
Does, if you had a bigger matrix, like a 5 by 5, there's no trick to lay things out to do that does not work.
Right, but sorry, we would do it the same way, but I'm struggling to figure out how to do it.
Yeah. So let me just, I'm looking back through my notes here. I should have, we did a bigger one somewhere, right?
Even that 4 by 4, I'm pretty sure I'll be able to
Yeah.
see how that works.
Yeah, that's what I'm looking for. Am I holding it? Oh, I'm holding it in my hand. That's why I can't find it. So yes, we can. Let's take this guy. Now I'm not necessarily going to do the whole calculation because it gets intense. But I'll show you a couple things, okay?
Yeah.
So number one, if you wanted to do this by cofactor expansion, it's perfectly legal to start here and say this is 1 times its cofactor. So you take out this row and this column, and you're left with 522, 389, 322. The next one will be negative. Then you take out the first row, second column, 222, 189, 122. Okay, I got the first two, plus minus plus, 1 times. Okay, first row, third column leaves 252. 139. 132. So we got plus, minus, minus is the last one. It's this entry. And I take out the first row, fourth column, I got 252, 138, 132.
And so they're nested into each other.
Yep. And then this one will produce 3 more of those. This will produce 3 more, this will produce 3 more, this will produce 3 more. You now have a dozen 2x2s, and those you could evaluate directly. However, let me point out that it isn't that bad, because if you just do some row reductions, say you went from this step to this step, then I suppose you could expand across this row right here. And this coefficient is 0, so you don't care what its cofactor is. This is -1. I gotta be a little bit careful here. This is plus, minus, this is a plus position. So -1 times, strike out that row and column, and then you're down to a 3x3. And then you could maybe do another row reduction, and you might knock it down to a single 2x2. So you can mix and match these things. So you don't have to do just cofactor or just row reduction. Or just row operations or just column operations. It's anything, anytime, you know, as long as you keep track. Okay, that's good. It's a good question. All right, now, I think we're approaching the end here. Let's see, have we done all that? Yes. Yeah, look at that. 1 page and we're done. Okay, Kramer's rule is named after the person who at least was credited with it, Gabriel Kramer. And there's a little bit of note here. And by the way, I did extensive research to find out this information by typing it into Google and clicking on the link to Wikipedia. So if you would like to reproduce my scholarly work, you can do that yourself. And by the way, some of the stuff is fairly entertaining. Also, let me just mention a pet peeve I have. I am a retired college professor, so I spent like decades hanging around other faculty members, and I got so tired of my colleagues griping about Wikipedia as being a terrible source for research. One of the reasons this appears here is because I started looking up articles in Wikipedia on subjects I know something about. And guess what? Time after time after time, the Wikipedia article, frankly, was not bad. Now, this does not mean that if you're writing a research paper, you know, you should cite 7 Wikipedia articles and you're done. No, that wouldn't be clever. But my personal opinion is that Wikipedia is a pretty reasonable source. And when you're getting started in a subject, you know, a lot of times the question is, what are the questions I need to be asking? And I find that things like encyclopedias are actually kind of helpful for that. And you just don't tell anyone you read it. Find another source for everything you say. You know, if people are that prejudiced against it, but I don't think that they should be. It's worth, I think, usually worth reading. Okay, so Kramer's rule, what does it say? This is a formula here, which tells you precisely what Kramer's rule says, but I think if we do an example, you will understand much more quickly than if I march through all of that theoretical description. It's not that the theoretical description is bad. I think it's extremely helpful. However, I just know, because, you know, I spent a lot of years as a student myself, that if I'm trying to understand a new idea, it's usually a whole lot more helpful to see a couple of examples and then see the general description. And then I say, oh, I see. Now this is like too weird to be true, but it is true. It works. It's amazing. So suppose we want to solve this system of equations. Now, honestly, it's not that hard. We could put this in our calculator and find out the solution, and that might not be a bad idea, because for one thing, I'm going to want that in my calculator anyway. So let's get this one in here. Minus 1, 2, 3, 2, 5, 6, 9, 8, 7. And double check. 1, 2, 3, 2, 5, 6, 9, 8, 7. The reason I want that, let's give these all names. AX equals B. Sooner or later, I'm going to want this number. What is the determinant of A? And since I got it in my calculator, I have a pretty efficient way of getting that. Matrix math determinant of A, and I get 6. All right, now we could get the solution here as well. Since this determinant is 6, it's not 0, and if a matrix has a non-zero determinant, it is invertible. Therefore, I can solve it this way. Let's get B entered. And that's a 3 by 1. Minus 3, 0, 11. And checking. Doesn't it? Forgot to do the quit. Minus 3, 0, 11. Okay, so a solution can be found this way. This is not Kramer's rule, but this is a fact. X equals A inverse times B. So let's compute that with a calculator, just so we have the solution to check with. Second matrix math inverse, where are you? Did I miss it?
That's how you use the X is -1.
Oh, I forgot. You're right. Matrix A, compute the inverse, multiply by matrix okay, 1, 2, minus 2. That is supposed to be the solution. And we could just sort of hand check this first one anyway. Minus 1 plus 4 is 3. 3 minus 6 is minus 3. How about the next one? 2 plus 10 is 12. Minus 12 is 0. Looking good. So I think we got the solution here. All right. Now, here's what Kramer figured out. He said, you've got 3 variables, x1, x2, x3, that you're trying to solve for. Here is how you get x1. I'm going to have a fraction in each case. Now, the denominator is just the determinant of A. And it's going to be that for each one of these. but the numerator is a matrix that comes from A in kind of a clever way. What he did is this. He said, okay, take this right-hand side and plug it in to this original matrix in the X1 column. Leave the other columns the same. Compute that determinant, and this thing is supposed to come out to be 1. This one, you do the same thing, except you take this right-hand side B and you plug it into the X2 column. And the third one, same deal. You start with the original coefficient matrix, replace its X3 column by the right-hand side. You know, who would even dream that a thing like this would work? But it's supposed to. So let's try. Now, we already know the determinant of A, right? So let's get the determinant of this matrix here. So we got 6 down there. All right. I don't want to do a whole lot of retyping. So I think what I'm going to do is this. I'm going to take a copy and store it there is a store key somewhere. Ah, right there. Store C. Okay, so I got a copy of A in C. And I'm going to change that first column to -3. Zero. $11. Make sure I got it. All right, now that is this matrix here, and I want its determinant. Six. A lot of work. But sure enough, it is 1, and that is the correct solution, right? And in the same way, you can compute these determinants, take the ratios, and you should get just what we have here. So in this case, I know the answer is supposed to come out to be a 2. So this must be 12. So it's 2. And this one's supposed to come out to be -2. So this must be -12. And of course, I could use a calculator or Octave or whatever to verify that.
So what's the benefit of doing that instead of reduced row echelon form?
For practically solving systems of equations, there really is no benefit. It's used in theory. And I think the primary reason it tends to be inserted here in this course is a little bit down the road. We end up solving a system of linear equations in the process of solving a differential equation, and we use this. So, to tell you the truth, I think that's it. And it might also be, there's a musical, I think Fiddler on the Roof, isn't there a song about tradition? Tradition. So why do I teach you this? Because I was taught it. So if I had to suffer through it, it's only fair that you do, right? And why did my professor teach me? Because he was taught the same thing.
Okay. Makes sense.
All right, I think, we're not quite done. Last paragraph. All right, the new and improved invertible matrix theorem. Now, we have not done a lot of theory so far. This is a theoretical statement, and this is something you definitely should know, all right? Because we use it over and over and over again. It's not just because we're trying to stuff your head full of theorems so you can forget them later, but because these are really helpful. Okay, the following 7 things are equivalent. The matrix A has a multiplicative inverse, A inverse. Now that automatically means it's square, right? So we're talking about square matrices. The row reduced echelon form of A is the n-dimensional identity. AX equals B has a unique solution no matter what you put on the right-hand side, B. The homogeneous equation, AX equals 0, has only the trivial solution. The null space of A consists of a single vector, the 0 vector. The rank of A is n, and the determinant of A is not 0. I don't know if I ever defined rank of A in lecture. It's in these notes somewhere. Here's rank, the rank of a matrix. There's more than one way to define it, but this is a good working definition for now. Start with a matrix, reduce it to row reduced echelon form. How many non-zero rows do you have? That's its rank. So the idea is it's sort of the number of rows that have non-trivial information in them. If you have a row just full of zeros, you know, that says if you take 0 times every variable and add it up, you end up with 0. Well, gee, how important that is. We knew that that's true no matter what system you're working on. So rows of zeros are sort of counted as not very important. So the rank of a matrix is you compute its row reduced echelon form and you count the number of non-zero rows. By the way, that would be exactly equivalent to saying you compute its row echelon form, not reduced, and count the number of non-zero rows. That's the same. You have a row of zeros in the REF if and only if you have the same row of zeros in the RREF. The big difference is the RREF is unique. The REF is not unique. And I thought further, I'm sorry, I can't think of your name. Okay. You asked, can you get the REF out of Octave or MATLAB conveniently? And I gave you one answer, which wasn't great, but it does work. Learn to do row operations one at a time, and you can row reduce. Option number 2, you can compute the LU factorization of the matrix, and that means a lower triangular matrix times an upper triangular matrix. L and U, lower, upper. U is darn close to the REF, not quite. The leading element in U will probably not be a 1, but let's say it were a 3. You just divide that row by 3 and you got it, okay? Yeah. So if you do an LU factorization and pull out the U, you're almost there. And what is an LU factorization? Oh gosh. I really am not exaggerating here. books could be filled with the stuff that comes from linear algebra. And the LU factorization is actually important, but there's really not time to talk about it right now. So, by the way, let me say just one last thing before we close. I'm done here, and of course, questions are fine too. But I, in the notes, suggested a book to read as a first pass in linear algebra. It's a very old book. It was published in the 1970s, but it's in your, listed in your syllabus. It's called Elementary Linear Algebra by Howard Anton. Now, Anton's textbook went through, I don't know how many editions. I think it's still in print. So, you know, could easily be up to like 14th, 16th edition at this point in time. There's an unfortunate thing that happens with textbooks. I've noticed this with calculus books, just as with linear algebra, and it probably happens across the board. Somebody comes up with a good way of teaching a subject. So they write a nice compact little book, highly readable, highly effective, doesn't teach you everything, but it teaches you enough that you get the lay of the land, and now you can learn more stuff as you need it. Okay, so it makes a great book. Then they market it, they sell it to a publisher, and the publisher sends it out to people like me. And you know, all of us read the book, and we write back a little report, and we say, yeah, it's a great book, very unique perspective, thought it was really helpful. I'd be happy to adopt it, except it doesn't have my 2 pet topics. And so then the publisher kind of picks those 3 or 6 or 8 topics that got mentioned the most by the book reviewers. And they say to the guy, okay, this is a good book, but you got to put these topics in. So he puts in 2 or 3 or 8 more chapters. Well, then they market the book, and because it is a good perspective, it sells. And then they decide they want to go to another edition. So they send it out once again to people like me who, you know, what do we know? We're just using textbooks. So we write back and we say, you know, I'd be happy to use this book, except you didn't include my 3 pet topics. And so they insert some more. And this is literally true. If you look, stack up editions of a textbook, they start clean, compact, easy to read, and they turn into calculus books, which nobody reads. They only use them as a list of problems. So this has happened to Anton. So do I really think that the 1975 edition is the best one? Well, not necessarily. If you buy the 3rd edition instead of the 1st, it will be fine. But the key is you can buy the 1st or 2nd edition. I think the one I have is 2nd. When I bought it, I paid more for shipping than I did for the book, okay? So if you can find one, it's great. It's an easy read. You will understand linear algebra when you get through. And I think it's a great book for that reason. Now, the problem with it is that it's rather dated. So after you have done this, you now have a good sense in your head of what is a vector space and why would anyone care? Okay, so you now have that information tucked away between your ears. Then maybe the next one I would read is by, shoot, I can't think of his name. He's from MIT. Anyway, Gilbert Strang, S-T-R-A-N-G. Gilbert Strang has a pretty modern treatment of linear algebra, but he did the same thing. He came up with a new, fresh way of looking at the topic, and it's a great book. So I would read that one next. You'll find it's dramatically different from what I'm doing, but it's also very, very useful. And the reason I'm doing this is because I'm trying to give you enough linear algebra in a short period of time that you can actually take it away and use it. But, you know, I'm not even close to exhausting the topic. And Strang does great things in his book. I strongly recommend it. Then Strang wrote another book called Linear Algebra and Differential Equations. And that would be a great one to follow up on. And if you read all of that, with understanding, you would probably know more about the subject than I do. This really is not my field, but they said, will you teach this course? And I said, will you pay me? And they said, yes. So I said, I would love to, absolutely. Okay, so that's the end of my pearls of wisdom and numerous arithmetic errors for one day. If you didn't already, you want to drop off your paper before you go. And if you didn't already, please remember to send me a copy of your paper by email. Okay, any last parting questions? All right, if you are done talking to me, as I am done talking with you, you can indicate that by leaving. When you're all gone.
Thank you.
Thank you. You're welcome.